So let's go to brain. Brain, 10 to 11 neurons, 10 to 4 synapses per neuron. We have 0.2 spike per second each neuron generates, and we consume, in general, the one of us who are thinking, maybe 20 watts, okay? And the power efficiency is 10 to 1,000. We can compare giga-synaptic operation per second, like a computer operation, okay, just roughly, okay? One very powerful computer nowadays, it has a power efficiency of 5.27 gigaflops per watt. So you can look the difference, okay? So our brain is a very powerful machine. Simply, we have to try and to understand. We are exploiting it in our daily life, but we can use it also for other purposes. Okay, question about DNA? So I hope that the first example of flip-flop can be something fancy, but this example, it is a thing, because really demonstrates you that it can work. So DNA, it is simpler than enzymes, okay? Enzymes, you see, they are good guys. They really do specific job. And another important property of biomolecule, it is that they are very efficient, reliable, and how you say, precise. The enzyme, the restriction enzyme, doesn't cut where the sequence is not the good one. They are reliable. Selective, very much selective, this is the word that I was missing. So enzymes are usually used in nature as catalysts most frequently. Most of them are proteins, okay. Also there are some catalytic RNA molecules, but this is, I took it from Wikipedia, it's not important, but just to understand what they are. And the enzyme, I know Yuval told you already something, or that the enzyme, it has a substrate. The substrate, the reactant moves toward where the enzyme site. The enzyme catches it, and then the presence of this substrate or reactant triggers a chemical reaction. And for example, in this case, something happens. In this case, my reactant, it is cut in two parts, like to be, for example, in case of DNA, I have a strand, the enzyme catches the strand, cuts it in two, and I have my two strands separated. This is what the enzymes usually do. Let's see how I can use a bioelectronic device controlled by enzyme. And this is, again, written by Evgeny Katz. The advantage of using the enzyme system, it is that usually I measure the concentration of my enzymes as information. They can be, I can do it optically, electrochemically. The point is that this happens usually at low levels, okay, of concentration. But so I need highly sensitive techniques. So it is good, but of course it is expensive in terms of technology. What is good from enzyme that they are catalyzers, so they amplify in some way, okay, the reaction that I want to use and catch. Most frequently, usually the enzyme-based logic system, they produce a change in pH. Again, another thing that I can measure, like a digital value 1, 0, or something similar, okay? So, let's see. Some examples. Again, let's see some examples that I can use for building AND or OR gates. Let's start looking for an AND gate. If I want to build an AND gate, in this case, in this experiment, and after we will see also results, they use sucrose. They use the sucrose hydrolysis, biocatalyzed by this enzyme, the invertase. ACE, what ends with ACE usually is an enzyme. Okay. Then I have also glucose that is oxidized by oxygen. If I have glucose oxidase, another enzyme that is very, very famous and used. Then, because of this reaction, we will see it in a plot, I create gluconic acid. The gluconic acid, of course, is acid, so it decreases the pH. So the change in pH tells me if the reaction happened and the AND gate was applied. And now we see how an AND gate is possible to obtain an AND gate. It is possible to have the AND gate because I have my biocatalytic reaction producing, okay, the acid, if the two elements are present together. If just one of them is present, it doesn't work. Let's go to the plot, it's easier to understand it. Okay? So I have my glucose oxidase, I have my invertase. If I just have invertase, I do not produce sucrose. If I adjust the glucose oxidase, I don't produce sucrose. If I have both of them, I produce what was written here. So I produce the, where is it? From the sucrose, I produce the gluconic acid. So from this reaction, it is produced the gluconic acid, and so the pH decreases. If I have just one glucose or glucose oxidase or invertase, it is not produced the gluconic acid, and so the pH doesn't change. So this means, okay, and I need both of them. So again, one means presence of glucose oxidase, one means presence of invertase, 0 means not presence of one of them, and so is an AND gate. What is appearing here that is important, it is that now in my solution I have gluconic acid. So it's finished. It's no more running because it's already a pH is down. So I have to reset. In all the biological reactions like this one, you have to reset. And in this case, you use urease that will, let's say, destroy the gluconic acid and will reset the pH to the standard value. So your gate is ready to restart again to work. These are the measurements done, you see, with as input A, B, or C. So not glucose oxidase, not, what's the name of the other? I forgot it. Not invertase, or none of them, A, B, and C, the pH remains constant. If I put both of them, of course, you see, minutes, okay? So after minutes, I have a reaction and I have a result. And this is a normalized plot of, the plot of change in pH, okay, after 20 minutes about, I have this change in pH, okay? So it works. Again, not so efficient, but it works. And I'm able so to build an AND that has as input invertase and glucose oxidase, and urease is the reset. This is the picture of my gate. I can also build a OR. For building an OR gate, I can exploit the hydrolysis of ethyl butyrate that is catalyzed by esterase. And again, I use glucose that is biocatalyzed by glucose oxidase. In this case, I skip these details because I hope it's clear. Glucose oxidase produces butyrate acid. This is another acid generated by the reaction between glucose oxidase, ethyl butyrate, glucose. So I generate, it generates gluconic acid. So I have gluconic acid if I have glucose oxidase. I have butyrate acid if I have esterase. So in both cases, I produce an acid. If they are both present, of course, I produce both acids. And so this is an OR, because if glucose oxidase or esterase are present, I have a decrease in pH. For me, the decrease in pH means 1. Okay? And after I have urease for resetting everything. And you see here, of course, the change in pH is not proportional because there are two different reactions. So the first reaction depends on glucose, or the other one on esterase is different. Of course, I have a highest change if both are running, so I add more acid, okay, inside my solution. But in any case, you see, in respect to not having any of them, the difference, it is very much evident. So this is what, and this is again the esterase, the glucose oxidase in a OR. Urease again is used as reset. As readout, usually are used electrochemical cells. In this case, it is used capacitive electrolyte insulator semiconductor for measuring the change in capacitance in this case. But I have several possibilities. This is what was used in this case. And here are, okay, the different changes in capacitance depending on the different, on the two gates. So you see, after the reset, again, biological system, I don't come back to the real zero, okay? The biological systems are more complex and less, okay, precise, but it works. But I can also do a logic network, putting together in a smart way different chemical elements and different enzymes. In this example, it was used ADH, alcohol dehydrogenase. It was used as enzymes. So there were used three enzymes: the glucose dehydrogenase, GDH, and again, the glucose oxidase, I tell you, it's used because it's the most famous and stable. And then, as inputs, I use acetaldehyde, I use NADH, nicotinamide adenine dinucleotide, I use glucose, and I use oxygen. I have 4 inputs and 3 that are the enzymes that are my working system. So here you see the acetaldehyde in presence of ADH, it is generated this complex, and you see I have an ADH in presence of ADH, it is generated NAD+. The generation of NAD+ in presence of GDH generates back again NADH, so it's a loop, okay, looping reaction. If I have glucose, because of GDH is produced gluconic acid, so the pH is decreased. Or, from the other side, if I have glucose and glucose oxidase, we know that we have a pH, but this is done only if I have oxygen. So you see, what I was telling you, I use OR, I use AND, exactly in this way. If I have an ADH and acetaldehyde with ADH presence, of course, I have to put it. I do AND these two, that I produce an ADH, but an ADH is in AND with the presence of glucose. At the end, it produces, yes, an acid, an ADH plus an acid, gluconic acid. From the other side, if I have oxygen and glucose, I produce again a gluconic acid. So the two exits are in OR, because I can have a production of gluconic acid from this side, from this, let's say, path, or I can have it from this path. So you see, I built here a logic network. Okay? So you can imagine now it is a matter of fantasy. You just have to put together, and you, again, everything is done in parallel. You put everything together and you wait the time to have a solution. The readout system, in this case, it is based on cyclic voltammetry, okay, that was introduced you by Yossi Shakam. Here, before I prepare these some slides in electrochemistry, but I skip them because I want just to arrive to the point. We have the several chemical cells, okay, but you have this presentation in case you need it. We have oxidation, of course, and reduction is the basic of my exchange of electrons, because in an electrochemical cell, I read the creation of current on my working electrode. So depending if I have a reduction or an oxidation, I have a release of a catch of electrons, I measure a current. Of course, the next equation gives us the concentration of what I want to detect, okay, related to the electrochemical cell. I can use potentiometry, I can use colorimetry, but voltammetry is the most used, and voltammetry, it is like this. The voltammogram is based on the fact that if I have in solution the species that I want to detect, I have a current because I have a reduction or an oxidation on my elements, on my molecules. And so I read a current. And so I can have my voltammograms, I skip them, and I use as basic circuit a potentiostat for reading my current using here a transamplifier, okay? A transimpedance amplifier. Okay, I went shortly, but because I want to see what these guys did in this experiment, they did the voltammetry, and so you see that only if I have final end, so it is I reach a 1 at the end of my combinational network, I have a peak of current. Else, in other cases, with I have A, so off state, no input, or okay, a 0 out, I don't have any current. And these are, you see, I have a few combinations of my input that give me a 1 at the end, and you see here the difference when I have my inputs or when I don't have them, and this is the exit on my cell measured by the current, because I'm doing an electrochemical cell measuring the output current. There are bad news that I want to give you. Okay, the enzyme-based are robust and error-free because the enzymes, they are really, really reliable. The limit is that there are cross-reactions among different enzymes, and so the problem is to design a system in which the enzymes do not react each other. So I lose and I miss the reliability of my system. And so I have to do several wells, separate them, and so it can become a little bit complex. A very effective solution that can also be exploited, it is, so we move up again to complexity in terms of biological molecules, is to exploit the antigen-antibody reaction. But what I finish here, again, coming back to enzymes, what some colleagues did in this case, they put in the same solution several enzymes, of course, designed in the right way for detecting soft injury tissue, traumatic brain, liver injury, abdominal trauma, hemorrhagic shock, oxidative stress, and the problem was that a mix of all these injury detectors gives you back the fact that the patient has problems or is ill. Okay, just one of them is not enough, is not sufficient. So it's a mix, it's a network, it's a combinatorial network, you say, a logic network putting together all these systems, all these information and injuries. I don't go in details because it is not the case. What I want to show you in this example is that these guys really built a very complex system, okay? And I want to go just in details of this first cascade where they built a NAND gate, okay? NAND gate, for microelectronic guys of you, working more on digital gate, means that NAND is the universal gate. So with NAND or NORs, are the two universal gates, I can build a Pentium. I can build everything. Of course, not with the performances doing some more optimized design, but now this is a final proof, and I like to use this as example, that in principle I can do everything. Just simply to choose the right things to put together. They did an electrochemical readout of 6 different outputs. Again, I don't want to go in detail. So they use these 6 different information extracting, because the injury code, it is related to the fact that STI is 1, ABT is 1, and all the others are 0. This is a coding that tells me, okay, I have an injury, I have a problem. And so they did this for proving that also they were able to detect, if you can name it, there is intelligence here, because it is an algorithm that is applied to a complex system for extracting the information I need. Everything done in a liquid solution, just waiting after minutes that I have out the solution.